Okay, in our accelerated math analysis, we're going to be taking some very important derivatives. Our learning target is I can take derivatives using the chain rule. The chain rule is for composition of functions. One function is substituted inside of another. Take a look at the very top here. If you had y equals sine of 2x, obviously you have sine of 2x, you could sine of x as one function, but you could have g would be 2x, and you're plugging 2x in, so that's your composition. Yesterday we learned that the derivative of sine is cosine, so it's very tempting for us to think, I think most kids would believe that your derivative would be the cosine, and then perhaps of 2x. Your calculator can confirm whether we're right or wrong, however. What we can do is go to y equals, and we'd like to take a derivative of this function. So if we go to math, and if we go down to 8, when we hit n deriv, you'll have d, well, we'd like to say x, take your derivative with respect to x. We'll take the sine of 2x. And finally, we'll say, we'll find this derivative at a particular value. We're going to type in x right here as well. This means take the derivative of the sine of 2x for every x, and let's see what that graph looks like. You might think it looks like the cosine of 2x. Let's take a look and see. If we did zoom trig, at first glance, we're going to look at this shape, and this is graphed between negative 2 pi and positive 2 pi. Usually kids remember x-files, that if you have a 2x on the inside, that's going to affect all x coordinates. Dividing it by 2, it will shorten your period with reverse logic, so you're going to have one period going from 0 to pi. And you do have that cosine shape, but look at the amplitude. The amplitude is actually a 2. So we have very good reason to believe that that would be cosine of 2x times 2. And right here is the rationale that we're always going to have. When you are dealing with a composition of functions, when you have one function substituted inside of another, take the derivative of that outside function. That's what we did here. The outside function was sine. The derivative of sine is cosine. So take that derivative of the outside function, that's f prime. We're still going to have the same argument, the same term inside of that outside function. We'll have f prime of g of x. You have the cosine of 2x. But then you take the derivative of the inside. So the derivative of the outside multiplied to the derivative of the inside. We're going to skip number 1 for the moment and come down to number 2. And at first glance, as we look at this problem, I think it is very, very tempting to think we must use the quotient rule. That being said, if we were to raise 1 minus 2x to the top, our new power would be negative 3. This is preferable. If you can rewrite a fraction as just an expression to a power, then you don't need the quotient rule. That being said, I hope you can see that we do have a function on the inside raised up to the negative third power. That outside function is that negative third power. So according to what we just saw, we're going to take the derivative of that outside. We're going to bring down negative 3. We'll have 1 minus 2x. We subtract 1 from our power, and we'll have negative 3 times 1 minus 2x raised to the negative fourth. But then we have to take the derivative of that inside portion. The derivative of 1 minus 2x will actually be negative 2. Just simplifying, negative 3 times negative 2 is actually a 6, a positive 6. You could bring down that 1 minus 2x, raising it to the fourth, and you're done. You found your derivative. This would allow you to find tangent line slope should you need it. Take a look at number 3. Please remember that the derivatives of all trig functions require us to be in radians. Now, what we're going to do is convert x degrees into radians. We're going to do a little bit of work off to the side. So remember the link between degrees and radians. We know that 180 degrees would equal pi radians. Even put a little r up there. It wouldn't take you too much to realize we need to put our degrees down below to get them to cancel out. And when you do that, you will be left with pi over 180 times x, and that's in radians. That's the inside of our function. That d sub x means take the derivative. Like I said before, if we're taking a derivative, we have to take that derivative with our function in radians. I hope you can see, much like our beginning problem, there is an outside function, that's cosine. We have an inner function, that inside, what's been plugged inside of it, is pi over 180 times x. So let's take our derivative of this outside. What's the derivative of cosine? Negative sine. And we still have that inside portion. Then we're going to multiply by the derivative of that inside part, and we'll get pi over 180. The derivative of pi over 180x, well, x to the first always disappears. Your final answer will be negative pi over 180 times the sine of pi over 180x. You can see it's preferable to take derivatives when you have your trig functions in radians already. It's not fun to take derivatives of functions in degrees. Well, let's take a real quick look at number 4. As we're looking at number 4, this problem might seem a little intimidating, and I think the reason why is you can see that it looks like we're going to need to do the chain quotient rule, and it certainly would appear so. What I'd like to encourage you to do, though, is whenever you've got a problem such as this, especially with trig functions, see if you might be able to rewrite it more easily, and maybe, just maybe, a derivative will become far simpler. Cosecant, I think most of us would agree, is 1 over the sine function, so it's 1 over the sine of 2x. Cotangent is really the cosine of 2x over the sine of 2x. Now, at first glance, this looks to be way worse than what we originally started with. We have complex fractions. But like we've been doing all year long, we're going to multiply by that LCD. And when you do, the sine of 2x will cancel with this one. You'll just have a numerator of 1. Down below, we'll have the sine of 2x plus, and now when we multiply here, the sine of 2x's cancel out. You're left just with the cosine of 2x. So I guess what I'd really like to point out to you is that we're supposed to take the derivative of this function here, but much like we did for the very first problem that we looked at, if you have the option of rewriting a fraction as a power, please do so. You'll avoid the quotient rule, and you're going to have a much simpler type of a problem. So right now, very much like the problem that we began the lesson with, we'll take our derivative of the outside. You can see on the outermost we've got a -1 power. So we'll say y prime is -1. Then we'll have sine of 2x plus the cosine of 2x And we're going to have to raise that up to the negative 2 power. But this is where it's going to get a little bit crazy. We're going to have to take a derivative of the inside. Now, when you're taking the derivative of the inside, there are two parts that you're going to have to worry about. And I don't think I need to even tell you, you're going to need to do the chain rule for each of those derivatives. So as we fix this up right here, the derivative of the sine of 2x is going to get you cosine of 2x. The derivative of sine is cosine. But don't forget, you have to take the derivative of the inside there. You'll get a 2. The derivative of cosine will be negative sine of 2x. But you'll have to take the derivative of that inside. So out comes a 2 as well. And you can see where we are right now. Having to take that derivative of the inside, it was like a brand new problem. It's almost like that could have been our first example, just dealing with that inside portion, saying take that derivative. And maybe that's a helpful way to look at it. But hopefully you can see negative exponents mean bring those terms down. So I'll have sine of 2x plus cosine of 2x. And I'll raise that to the second power. Here I've got negative 1. And we've got 2 cosine of 2x minus 2 sine of 2x. And tell you what, we factored out a negative 1. We might as well factor out this 2 as well. We'll have negative 2. Then we'll have the cosine of 2x minus the sine of 2x. And that's all over sine of 2x plus the cosine of 2x squared. Okay, well, let's see if we could get started by looking at this next problem, the very last one on the page. And this is by far the most complicated of all the problems. For example 5, I hope you're going to see that honestly what is really going to be happening is you've got 3 functions composed, not just 2. And that's going to make life a little more challenging. What I'm getting at is this. You could look at that square root as a 1/2 power. So you could say that this is 5x raised to the 1/2 power. Obviously, we have an outside function, that's sine. But on the inside, we have a square root, but inside of the square root, we have a 5x. So it's kind of like f of g of h, really multiple functions being plugged in. So how do we deal with this? What can we do? Well, take the derivative of the outside function. That would be cosine. Now keep that inside in here. You'll have 5x to the 1/2. If it's helpful, maybe right now you could think of this as saying, now I have to take the derivative of the inside. And yes, that derivative of the inside is going to be more complicated, of course. But now it's like a brand new problem. It's like me just giving that to you and saying, can you work that thing out? Well, let's do that as if it were just a brand new problem. If you were taking the derivative of 5x to the 1/2, you take the derivative of the outside. You take 1/2 5x to that negative 1/2 power. Then you take the derivative of the inside. And the derivative of the inside is 5. So let's clean it up real quickly. You have a 5, you have a 2, so we'll have 5 all over 2. Up on top, you'll have cosine. And 5x to the 1/2 power is the square root of 5x inside of cosine. And then you look at this negative exponent. That drops down to the denominator, but it's going to be a square root. So we have the square root of 5x. And that's it. For homework,